In a few minutes, you'll click on a link that will take you to this article in Amplify that you're going to be reading. Remember, you're using those active reading skills that you just went over previously in the Google Forms so that you're really getting the information down. What I'm just wanting to show you real quick is how to utilize the different resources that you've got in Amplify that comes with articles. Usually it'll pop up like this. If you're someone who likes it to be chunked into smaller bits of information, it can go to pages. You'll see what page number you're on down here, and you can go back and forth at the bottom. I personally don't like that, so I'm going to go back to not having it like that. The other feature that you guys will want to utilize is you can save your annotations in here. So say that you thought this one piece of information was important. All you need to do is hold your cursor over it and highlight it. You can just leave it as highlighted. You could also enter a note here. Say, I'm just going to, for example, say important. That's just an example. And then you should be able to, up here, look through your different annotations and notes, depending on what you're looking for. So that would be helpful in trying to navigate this, and also to make sure you really are getting those pieces of information that you need. I suggest, again, having this pulled up on one half of your screen and then the Google form on the other. If you're good to go on reading this on your own, you can pause this video at this time and go through completing your active reading of this article. If you're someone who would like for it to be read to you, there's a sound option here. And just in case for some reason your Amplify link is not working, I'm going to continue and play that reading of this article in this video right here. So again, if your Amplify link is working, you can pause this video. You don't need to watch the rest. If it's not working and you want the article read to you, you can keep playing this video. I'll do it in here right now.
Investigating landforms on Venus. Imagine traveling in a spaceship toward the surface of the planet Venus. At first, everything is hidden by thick clouds, but as you get closer, you can see the rocky surface below. As you fly over the surface, you notice strange landforms scattered around. They are raised domes with cracks reaching outward in all directions. These are called novae. Why do we see novae on Venus but not on Earth? Geologist Taurus Garia wondered whether two important differences between the two planets might help answer that question. First, Venus's atmosphere is much thicker than Earth's. Its thick atmosphere traps heat from the sun, making Venus much hotter than Earth. The average surface temperature of Earth is a comfortable 14 degrees Celsius, 57 degrees Fahrenheit, while the average surface temperature of Venus is a scorching 462 degrees Celsius, 864 degrees Fahrenheit. Second, Garia thought that possible differences between the geospheres of Earth and Venus might affect how novae are formed. He didn't know for sure, but he thought that the top rock layer on Venus might be thinner than the top layer of Earth's crust. A thinner crust might allow melted rock called magma to move toward the surface more easily, pushing the surface upwards to form the novae. Garia wanted to test his ideas about how novae form on Venus, but how? Venus is millions of kilometers from Earth, and the novae there were formed millions of years ago. To test his ideas, Garia made a computer model of Venus. Models can help scientists like Garia get evidence about things that are difficult or impossible to observe, like the creation of landforms on Venus. Some models are made of physical materials, and others run on computers, like Garia's Venus model. When Garia made his computer model, he made it represent Venus in ways that would let him test his ideas. For example, he made the surface temperature of the Venus model much hotter than the surface temperature of Earth. He also made the top rock layer in his model much thinner than the top layer of Earth's crust. Garia programmed his model to show what would happen on Venus over time with this combination of a high surface temperature and a thin rock layer. If features like novae formed in his model, he would have evidence that he was right about how novae on Venus were formed. When Garia ran the model, it showed melted rock rising up from underground, pushing the surface upward and creating raised domes with cracks reaching out in all directions. When he compared the domes that formed in the computer model with the domes on the surface of Venus, he found that the domes in the computer model were the same size and shape as the novae that have been observed on the surface of Venus. Because the model results matched the real features on Venus, Garia was more confident that the ideas represented in his model were accurate.